Okay, welcome everyone to today's CDAC webinar. It's my great honor and privilege to introduce today's speaker, Krzysztof Wozniak from the Department of Chemistry at the University of Warsaw, Poland, where he is now. So he's giving this talk from Poland. Krzysztof has been pioneering the field of quantum crystallography, which he'll tell us about. He's also interested in this technique combined with high pressure studies, and he's done a lot of work over the years using various techniques to study charge densities in crystals of interesting organic, inorganic compounds, minerals, polymorphism, and interactions in pharmaceuticals and a wide range of other materials. And he also has helped develop new methodologies in X-ray scattering and neutron and electron diffraction. Krzysztof spent essentially his entire career at the University of Warsaw, where he obtained his PhD in 1992. He's now head of the Crystal Chemistry Laboratory and Laboratory for Structural Research in the Department of Chemistry, head of the Laboratory for Structural and Biochemical Research of the Biological and Chemical Research Center in Warsaw, and head of the Cryo-Electron Microscopy and Electron Diffraction Core Facility of the New Technology Center in Warsaw. He's been quite prolific. He has close to 500 publications, and we're delighted he's agreed to give us this talk and tell us about his new work in quantum crystallography. Over to you. Welcome.
Thank you very much. Thank you. First of all, I would like to thank you for your kind invitation to present this lecture. This is a great honor for me, and I will talk today about quantum crystallography. Here is a brief outline of my talk. After a short introduction on success of independent atom model and quantum crystallography, I will present multiple refinement of experimental electron density, illustrating this with 3 examples, combining quantum crystallography with high pressure studies of single crystal minerals such as Xianhualite, calcite, and natrohalcite. Then I will shortly explain the main idea of Hirschfeld atom refinement and will present our results focused on validation of this method. This will include hydrogen atom positions in small molecule organic crystals. Next, we'll talk about precision and accuracy of different quantum crystallographic approaches, on hydrogen atoms in hydrides, and about experimental studies of relativistic effects and electron correlation in gold derivative. Finally, I will talk about ICES and will finish off with some conclusions and acknowledgements. So let us go to the first point. Ladies and gentlemen, let's begin with fundamentals, with the procedure of routine X-ray structural investigations. When a proper single crystals are available, one can mount a piece on a goniometer head of a diffractometer and collect thousands of frames containing intensities of reflections, which are a function of several instrumental factors, which can relatively easily be taken care of, and the most important, which depend on the square of structure factors. Structure factors are sums of atomic contributions called atomic scattering factors, Fj, multiplied by this exponential term containing phases. Once we know phases from structure solution, we can calculate electron density maps and put atoms in the maxima of such Fourier series, thus obtaining a single crystal X-ray structure of a studied compound. In this kind of procedure, in routine X-ray structural analysis, individual atoms are represented by spherically averaged electron density distributions obtained by theoretical methods for isolated atoms in the ground state, and atomic scattering factors are just a Fourier transform of spherical atomic electron density. Independent atom model does not take into account changes in electron density distribution of individual atoms due to chemical bonding, charge transfer, long electron pairs, and other effects. So that's the simplest possible model of atomic electron density. As I write in my abstract, isn't this a big paradox that independent atom model of electron density effectively introduced more than a century ago is still the most common model of atomic electron density used in X-ray structural analysis? One would even say that its success has dominated the whole field of single crystal X-ray diffraction for the past century. When independent atom model was introduced by Bragg and Compton, Max von Laue was getting his Nobel Prize. Him, the Braggs, and their colleagues were using homemade pieces of equipment. You can see them in these photos, which could have hardly supplied qualitative information on diffraction spots. In consequence, the errors associated with the model of electron density were overshadowed by far larger diffraction hardware errors. However, within the past century, and particularly within the last, say, 50, 60 years, there has been an overwhelming progress in design and production of X-ray hardware, which is made for needs of both small laboratories and large-scale facilities. So now we have close to $1 million worth of diffractometers, sometimes even more expensive than this, maybe 10 or more million US dollars worth desktop synchrotrons, $1 billion worth synchrotrons, and probably a few billion US dollars worth free electron lasers. All these very powerful X-ray sources have very excellent optical systems. As I said, powerful X-ray sources, fantastic detectors, noiseless detectors, resulting in stunning quality of data. For a very long time now, errors associated with equipment are far, far smaller than those resulting from the wrong model of electron density used. I do not see much point in getting dear data and using poor model of electron density. There is something fundamentally wrong with science in this respect. So we try to go beyond independent atom model, and that is why quantum crystallography was introduced. The original definition of quantum crystallography was given by Massa, Carle, and Huang, who defined quantum crystallography as a collection of techniques for which crystallographic information enhances quantum mechanical calculations and methods in which quantum mechanics enhances the information available from a crystallographic experiment. And if you want to learn more about current trends in quantum crystallography, you can take a look at this review paper in Chemistry European Journal, which was written after a small discussion meeting at Nancy. For me, quantum crystallography is crystallography beyond independent atom model. This diagram is describing state of the art in crystallography. Still, 99.7% of all circa 2 million structures have been refined with independent atom model, and only a few thousands of structures with aspherical approaches to atomic electron density. In red are the methods I will briefly discuss in this lecture. This includes multiple model of electron density refinement and methods related to this multiple model, which are utilizing transferable aspherical atomic electron density models. These are free data banks of ready-made bricks of electron density, which could be used to reconstruct electron density in macromolecules and small molecules. No doubt that the most important method is Hirschfeld atom refinement and different versions of Hirschfeld atom refinement, including the periodic HAR and HAR combined with extremely localized molecular orbitals, particularly for proteins. We have our own version of Hirschfeld atom refinement and also our own version of Hirschfeld atom refinement atomic electron densities. The other methods are maybe less common. So let us now switch over to multiple refinement. Multiple refinement originated from the Fred Hirschfeld laboratory at the Weizmann Institute in Israel. There are a few different versions, and I will only discuss this one presented in the slide, which is so-called Hansen-Coppens approach, as it was published in this ActaCrist paper. According to this model, electron density in crystal is sum of atomic contributions called pseudoatoms centered at the atomic positions. And each atomic contribution has three terms: spherical core electrons, spherical valence electrons, and so aspherical term, sometimes called deformation term. This spherical core electron term is simply calculated using ab initio methods. Spherical valence electrons, they, as you can see, this term have population of valence electrons and contraction expansion coefficients. And up to this moment is like modified independent atom model, modified because it can be increased or decreased depending on this contraction expansion coefficients. But the most important is this deformation term, where we have the radial part and angular part. The radial one, these are normalized Slater type radial functions, a bit similar to those used in the model of electron density for hydrogen atom. And the angular part contains density normalized real spherical harmonic functions, which are illustrated here, with proper coefficients, and by taking them with this population coefficient, we can mimic any deformation of electron density in crystal. Once we've got this atomic electron density, we can Fourier transform it and get a spherical atomic scattering factor. Then we can express structure factors for our model of structure with this spherical atomic scattering factors. And we can, having collected X-ray data, we can minimize differences between those calculated structure factors for our models, between modules of them, or between intensities obtained for our model and intensity coming from experiments. So we can minimize, by playing with the model, we can minimize those differences. And that's the refinement of electron density. Once we've got this red parameters, which are simply can be obtained from the fit against high resolution X-ray data, we can say that we have established experimental electron density distribution. And this distribution can be analyzed with many different methods. Among crystallographers, probably the most popular is the one proposed by Richard Bader, called atoms in molecules. And it's based on a few important notions such as a critical point and a gradient of critical points and gradient of electron density. And the gradient is just the first derivative with respect to x, y, z, and the places where it disappears are critical points. And one can calculate the second derivative at the critical points, and depending on the sign of this derivative, we have either minima or maxima in electron density distribution. And we can do this exactly in the same way as we were doing studying shape of mathematical functions in our secondary schools. But in this case, we have 3 dimensions, so we have to calculate the Hessian matrix of second derivatives, which is dependent on the reference system. We can always rotate this reference system in order to get rid of this off-diagonal terms. Because this is the trace of this Hessian, which is independent, invariant to rotation. And this is Laplacian of electron density. Laplacian is very important in experimental studies of electron density, as this is our magnifying glass. As you can see in this example taken from this book, Chemical Bonding and Molecular Geometry, here we have electron density of free argon atom and in 3 dimensions in this plot. And as you can see, it's not easy to see where the electronic shells in this atom are present. And we have to calculate negative Laplacian values function. And when this function takes positive values, we have concentration of charge. And when it takes negative values, we have depletion of charge. So Laplacian is helping us to identify charge concentration and charge depletion. And the last important term, these are atomic basins, and again, we'll explain them using an example taken from the same book. And here you see electron density of ethylene molecule, which is planar molecule, and we have big maxima at the carbon atoms and smaller maxima at the hydrogen atom positions. And one can draw gradient lines starting from atomic positions. They go to infinity, and except those which join the given atom with the neighboring atoms, all other gradient lines, they do not, which belong to one family of gradient lines, they do not cross with other families of gradient lines. They are separated by zero flux surfaces. And when we can use these zero flux surface hypersurfaces to part electron density into contributions which belong to given atom. That's why it's called atoms in molecule approach, because by integrating these atomic basins, we can get their volumes. We can get, for example, integrated charge of atoms, or when we integrate charge times position, we can get integrated atomic dipole moment. And the beauty of these atoms in molecular theory is that it's all these properties are additive. By summing them, we can get, by summing atomic properties, we can get molecular properties. So directly from X-ray experiments, one can get moments of charge distribution, electrostatic potential, electric field gradient, gradient of charge density, and plenty of other one electron properties of electron density. And this pseudo-atom formula is also used to create data banks of ready-made fragments of electron density, as you can see here. And the most popular of them are those 3 which are named at the bottom of this figure. The first one was created by Christian Jelsch, is abbreviated Elman at Nancy, and the second version of this data bank was made by Dr. Domagawa, who was my former PhD student during his postdoctoral stay in Christian's laboratory. And the second one was UBDB made in laboratory of Professor Philip Coppens and Professor Paulina Dominiak took over this data bank and keeps developing it. It's at present it has abbreviation MAT and is being further developed in Warsaw. And the third one was created by Birger Dietrich and is called Invarium. And those fragments of electron density simply, it appears that when we take electron density of a given atom in the same topological environment, neighborhood, these values are very much alike. So one can transfer electron density from such data bank to given molecule and create like the average electron density distribution either in small molecules or in biological macromolecules. This is especially important in studies of interactions of drug moieties with their macromolecular targets. And because using this approach, one can get energy of electrostatic interactions calculated as interaction between two distribution of charges rather than point atomic charges. So here you see several examples of application of this kind of data bank approach, transferable aspherical atom modeling refinement, these are beautiful papers allowing to estimate an electrostatic energy of interactions. And now let us go to the first example, which is the Shanhua light under pressure and variable temperature. Here you see some references to this paper and other papers which were published before regarding similar topics. Shanhua light is a Chinese zeolite. It's pretty complex. It crystallizes in cubic capital I-213 space group, and its name means in Chinese fragrant flower. We have collected data using our silver source and also other high pressure data sets at Soleil in France and refine experimental electron density densities. And it appears that we can refine electron density under pressure measured in a diamond anvil cell equally well as for crystals outside diamond anvil cell. And that's the setup at the crystal beamline at Soleil. But what I want to stress is this diacetyl 120 DAC, which has very wide opening angle, reaching 120 degrees. And this allows to get far more data than using diamond anvil cells with smaller opening angles. So I will just show examples of results we have obtained with such X-ray diffraction data. Let us begin with atomic basins of fluorine anion. You can see here this atomic basin of this fluorine rotating and atomic basins of another fluorine ion. And in these figures, with green patches, we have projection of atomic basin obtained at this green thermodynamic conditions, means 1.1 gigapascal and 293 kelvins, onto the atomic basin obtained at ambient pressure and 100 K. So these green patches are showing us this how electron density is somehow expanding when we are changing thermodynamic positions. We can get charge, integrated charge, integrated volumes, and similar parameters. Here, when you take a closer look, you can see small changes of this atomic basin, because these are three atomic basins obtained at 1.1 gigapascal, 1.9, and 4.2 gigapascals. So that's the scale of the changes. These are not big changes. However, we can easily measure them and quantify them. And the same, I mean, here we have such projections of atomic basins from obtained at higher pressures onto the atomic basins and lower pressures. So we can see how electron density is trying to escape from this atomic basin when we start pressing it and when we start going to higher pressures. But we can look inside atomic basin. Here we see the differences in total atomic electron densities, and these differences are calculated. The contours are at 0.1 electron per cubic angstrom and minus 0.1 electron per cubic angstrom. How we could interpret them? In these blue fragments, there is 0.1 electron per cubic angstrom more at ambient pressure and 100 K than at 1.1 gigapascal and 293 K. And when we move to this higher pressure, in this red area, there is 0.1 electron per cubic angstrom more than at these blue conditions. So in this figure, we have shown relocation of electron density at a fluorine atom when we go from one thermodynamic condition to the other one. And we can see pure effect of temperature and pure effect of pressure. In this case, we take away from electron density at ambient pressure and room temperature, electron density at 100 K. And we can see that electron density is relocating from this direction towards calcium ions into the diagonal directions. However, when we increase pressure and from ambient pressure go to 4.2 gigapascals, we can see that electron density from these diagonal directions is localizing more or less along lines towards these calcium ions. So one can say that the effect of decreasing temperature and increasing pressure, those two effects are to a certain extent orthogonal ones. So we all got used to polyhedral representation of inorganic or mineral crystal structures, mainly because this kind of representations looks great, particularly at the structural level. However, at the level of electron density, these are very complex objects because they do not contain the full electron density or the full atomic basin of given central ion. And additionally, they contain small fragments of electron density of the corner ions. So at the level of electron density, it's far better to use atomic basins as they contain only electron density associated with given ions. So So maybe we should somehow change paradigms. Here you see fragment of electron density of langbeinite mineral shown in atomic basin representation. We can see how, from definition, these atomic basins are perfectly aligned one to another. When one applies pressure, we can immediately see how neighboring atomic basins are pressing a given one selected. Under pressure, all these atomic basins do change, and electron density is redistributing. Also, electron density is exchanged by ions. And new delicate balanced distribution of electron density is created. Of course, at the level of electron density, the main notions of classical crystallography or mineralogy are absent. We do not have any close or closest packing of spheres, as we do not have, as we do have irregular atomic basins instead of spheres. It's not difficult to define. It's really quite difficult to define, say, atomic radii or van der Waals radii. And as Pauling's and Goldschmidt rules are based on these notions, so maybe we should rethink them. We also somehow, of course, we do not have this independent atom model. But we are getting new tools which are very sensitive to interatomic interactions. Now, the second example of calcite. Calcite is very common mineral, is the most stable polymorph of calcium carbonate. Here you see the structure and independent part of the unit cell in this atomic basin representation. And it undergoes quite a few phase transitions, but we have focused our attention on the very first one, from calcite 1 to calcite 2, which is taking place at 162 gigapascals. So we collected the following data, which are summarized in this figure, starting from 0.85 gigapascals, going through up to higher and higher values. And then we switched over to monoclinic phase. Because this phase transition is displacive, non-destructive, and reversible, we can go down with pressure just to have confirmation of results. We are getting increasing pressure. Anyway, the data were collected at ID27 at the ESRF. It's an extremely good station, very well equipped, extra stabilized with Eiger cadmium tellurate detector, and is run by Mohamed Mezouar. And one can really focus the X-ray beam up to, say, less than 2 micrometers, which is very helpful because one can collect separate data sets from singular crystals. You can see a photo of diamond anvil cell and small tiny crystal of say 20 microns inside. And we've got very good quality data. I'm not going to discuss this tape, but I just want to show that we've got completeness close to 0.8, means 80% or better, and the residuals are very good as for mineral for refinement of electron density in minerals. And of course, we can get crystal structure and changes, all changes at the level of structure. But this is not fun. Real fun begins with this atomic basins. Here you see dependence of atomic basins on pressure, and they change a little bit. We saw how big could be those, or rather how small could be those changes. And there is a bigger change when we go to the monoclinic phase. But we have to find new ways of quantifying these effects, because these changes of shape do tell us something. They tell us about changes of interactions. These are the atomic basins for calcium ion. And in this case, when we go to the monoclinic case, we see new facets which are appearing in this atomic basin. So when we have phase transition, the change is big, but within given phase, the change is really gradual. The same for oxygen atoms, and where on phase after phase transitions, we're getting three independent oxygen atoms. And again, the changes are very small. So how to quantify them, how to detect them? So we can use this projection of atomic basin at one thermodynamic condition onto the atomic basin at another thermodynamic condition. So this is showing us somehow how electron density is expanding when we go from one pressure to another pressure. And we can look inside atomic basins by analyzing differences in total electron densities. And very often we have big changes at borders of atomic basin. That's why we have such blue hypersurfaces. But what really matters is the shape of these differences at a given atom, because this is showing us, and we can detect this and describe this at different contour values, just to see how electron density is relocating under pressure. We can get integrated properties such as charge or volume, and as we can see here, the charge of oxygen atoms is decreasing with pressure. We have a kind of metastable phase before we are getting this calcite to form. We can see that carbon atom is getting charge. The positive charge is decreasing with increasing pressure, and calcium is giving up charge. And again, clear manifestation of this metastable phase. We can actually deconvolute equations of states into atomic contributions. As you can see here, we are getting the volume, dependence of the volumes of atomic basins as a function of pressure. And we have negative compressibility of carbon atom, and because the volume is increasing with pressure, and normal compressibilities of oxygen and calcium. And we can really get far more details. For example, how electron density at the bond critical point is changing when we increase pressure. And also, but in the case of, say, contacts to carbon atom, we are not getting nice relations, but only very broad scatter of data points. We can also see how this critical point, this weakest point of a bond, is shifting with pressure. For example, in this case, the distance to calcium ion is decreasing, means this critical point is going closer to calcium and is slightly escaping from oxygen atom. And in the case of carbon atom, we see big scatter. And when we divide amount of electron density in given atomic basin by the volume of atomic basin, we see really very nice dependencies for other atoms than for carbon. Carbon is far more sensitive, is changing a lot. And this is why in the other relations we were having big scatters of data points when a carbon atom was involved. Now, a few words about tracing of mechanism of hydrogen bond symmetrization at high pressure by experimental charge density distribution in natural halcite minerals. This is, I would say, first of all, beautiful mineral. It forms this kind of emerald type crystals. And natural halcite gained importance in recent years as a potential anode material for lithium-ion batteries, which are used in powering different electronics and vehicles. There is very interesting, I would say, the key point in this mineral is bihydroxide unit, which is defined here. We have very strong, very short hydrogen bonding between two oxygen atoms with this H4B hydrogen atom. And additionally, those oxygens, they form rather routine hydrogen bonds to other oxygens in these crystals. A lot is going on in this hydrogen bonding. Again, we got excellent data from ID27 at ESRF for three very well-oriented single crystals inside DAC. That's what I'm stressing. Especially in the case of low symmetry crystals, one should orient them in DACs just to maximize the number of reflections available. And we've got pretty good data. I wouldn't say, I mean, the completeness is only 64 up to 70%, but this is monoclinic system. But the data are very consistent. The values are really, I would say, very reliable. When we refine this up to the very electron density, up to the very end, we can remove hydrogen, this H4B hydrogen, and keep refining further in order to see residual electron density in this hydrogen bonding. And here you see evolution of this position of residual electron density, and this hydrogen bonding is disordered, and degree of this disorder keeps changing with increasing pressure. Then it starts localizing at the center, and very strong symmetric hydrogen bond is created. We can look at this using negative Laplacian maps or differences in negative Laplacian maps. In this negative Laplacian maps, we see if at ambient pressure and at 0.6 gigapascal, clear two maxima confirming this disordered nature of hydrogen bonding. And when we increase pressure, we see depletion of electron density from this central point. And when we increase pressure more, these hydrogens, they localized at the center of symmetry, and with further increase of pressure, we have just more and more electron density at this point. Finally, a very strong ionic hydrogen bonding is created. This is deformation map, clearly showing flow of electron density through this bond. But even more interesting are maps of differences in negative Laplacian values. So from Laplacian distribution at 0.6 gigapascals, we have taken away Laplacian distribution at, say, ambient pressure. So we can see that at first, concentration of charge at this maxima is taking place, and depletion of charge in this blue area. When we go from 0.6 to 1.08 gigapascals, This process is strengthening. We have depletion, clear depletion of electron density from the center and bigger maxima. And when we go from 1.08 to 1.57, suddenly we have like a completely reverse polarization. We now are observing localization of electron density where we used to have depletion, and we see depletion of electron density when where we used to have polarization. And when we go to bigger pressures, this electron density starts localizing at the center of this hydrogen bonding. So with this kind of maps, we see more. And this is perfectly in line when we observe how volumes and charges of this hydrogen atom or oxygen atoms are changing. So the picture is very consistent. A lot of very interesting changes are going on at copper ions, but that's for another story. I have too short time today. So let's go to Hirschfeld atom procedure. Hirschfeld atom refinement is a method of refinement of structure and could be on its own, but also it could be the first step in the refinement of wave function. And in this refinement, we use so-called Hirschfeld or Stockholder partitioning of electron density. According to this partition, electron density of atom A at point R is the total electron density multiplied by weight. And the weight is the ratio of spherical contribution of atom A at this point to the sum of contributions coming from all atoms forming given molecule. So actually, this weight is a kind of a share. Atoms are shell holders, and molecules is a shell holder company. And we can, having this Hirschfeld partitioning done, we can Fourier transform this atomic electron density and get a spherical thermally average spherical Hirschfeld atom scattering factor, and, which is this F value here in this formula. And we can use this to calculate structure factors for our model of structure, similarly as we are applying pseudo-atoms after Fourier transformation. And this approach was introduced by Dylan Jayatilaka from Perth on this photo, and who wrote a code called Tonto. And for a long time, Tonto was the only software allowing this kind of computations. Then we can simply collect high resolution, collect data, X-ray data, diffraction data. It doesn't have to. This doesn't have to be high resolution, and play with the model and minimize the differences between modules of structure factors from our model and those from experiments. We can measure these differences by using chi-square test. So the whole procedure goes like this, that firstly we do routine refinement and spherical refinement, and we take this molecule and calculate molecular wave function. From this, sometimes we surround this molecule by multipoles to mimic the influence of crystal lattice. And then from wave function, we can get distribution of charge. Then we perform partitioning of charge into Hirschfeld parts, and And then we can use them and perform minimization. And after minimization, we are getting new coordinates of structure of atoms. So for this new coordinates, we calculate again molecular wave function, and we go in cycle until we get convergence. So this is computationally sometimes demanding, especially when we deal with big molecules. But it's very effective. In fact, we have our own software, which is slightly better than other pieces of software in this field. We have a DISCAMP library. This is abbreviation for Densities in Structural Chemistry and Molecular Biology, and which we use to calculate X-ray scattering factors. And the whole scheme is more or less the same, only we use other programs to get wave function, and in our software we have a possibility to apply more partitioning schemes. I mean, because this Hirschfeld partition is just one example of partition taken out of a bigger family of partitions. And we have written this software in order to be able to use other partitioning schemes. And just a few weeks ago, we have published also a paper about this kind of exponential or power Hirschfeld partitioning scheme. So this question, which partitioning scheme is the best, is still open. It's too little time to go into details, but this requires bigger studies. But when we get the final geometry, after performing this kind of refinement, Hirschfeld atom refinement, we can fix it and fix ADP's values. And in the second step, we can minimize this kind of Lagrangian, which is a function of molecular orbital coefficients and also a function of energy expression, which could be Hartree-Fock or Kohn-Sham. And as you see, we have also here a kind of coupling term, which is just a Lagrangian multiplier. And here we have this kappa, this chi-square value, and also desired agreement with experiment. So in this step, we do minimization of energy, and this is probably the very first method in X-ray crystallography in which one is minimizing energy, not only just performing least square refinement. And the beauty is that we can use full power of quantum chemistry. I mean, here's just example, but of course we can use DFT, we can use Hartree-Fock, we can use a couple cluster, absolutely, or even bigger, better levels of theory, depending on time, on money we have to perform calculations. We can use different basis sets proper for given problem, for given atom. And I can answer that we spend a lot of time on trying to find the best combination of different parameters. And unfortunately, we haven't found the best combination. It means that for each problem, we have to find separate the best combination of theory with basis sets, with say including environment, etc., etc. So we spent a lot of time on validation of HAR, and I will show you some examples. And we'll begin with hydrogen atom positions in small molecule organic crystals. We have performed a large-scale study by applying HAR to 81 published crystal structures of organic molecules, which we retrieved from a Cambridge Structural Data Bank and reuse by simply applying HAR to these structure factors which were deposited in Cambridge Structural Data Bank. And next, so this is the refinement strategy. So we did it for two resolutions, for maximum resolution and then for worse resolution. And for this 81 crystal structures, we've got hundreds, if not thousands, of different types of bonding to hydrogen atoms. We categorize them in the way Allen and Bruno did in their papers. Many crystallographers were using their papers when they were standardizing or normalizing hydrogen atom positions. This means when they were trying to get the best refinement by simply elongating bonds to hydrogen atoms. So they were taking the neutron values of these bonds from this paper and previous paper by Allen and Olga Kennard. So here you see the results. We compared our results with neutron data. So there are only like 4,500 of neutron structures, and when you focus your attention at the very best quality single crystal troubleless structures, you can get different types of bonding to hydrogen atoms, as this is enumerated here. So these are different classes of bonding to hydrogen atoms. And this blue color is showing distribution of neutron values. This deep red is showing results of resulting distribution of the same bonds obtained from HAR for maximal resolution, and deep green for resolution cut to 0.8 angstrom. And this light rouge color and light green are showing independent atom model refinement. So no doubt that Hirschfeld atom refinement for all possible types of bonds to hydrogen atoms is giving almost neutron quality bonds and far better than independent atom model. So that is showing the importance of HAR when hydrogen atom is involved in problem. We also perform studies of precision and accuracy of quantum crystallographic approaches using oxalic acid. And we kept collecting high-resolution oxalic data for a long time, and finally we used them to study accuracy and precision. How do I understand accuracy? In science, we do not know the true values of parameters, and we'd never know them. With different techniques are showing us only better or worse estimates of those true values. So the true accuracy is unknown. But in the case of, for example, bonds to hydrogen atoms, we know that neutron data will be giving values closer to the true values than X-ray data. So we can have a relative accuracy as a difference between, say, if we collect multiple data sets between average values from X-ray diffraction and those from neutron diffraction. And of course, when we get multiple measurements, we can have estimation of precision by using sample standard deviation. And that's what we did. And we've got like 13 charge density data sets for hydrated oxalic acid. And that was a part of PhD thesis of Radek Kamiński. And then we reuse this data by cutting off fragments of resolution and reprocessing them from scratch in order to get dependence on resolution and on model of atomic electron density used. So you can see results in those two papers. So for example, let us take just the central C1-C1 bond. And this is dependence on resolution. And that's maximal resolution is here. And these triangles, squares, and cycles are showing the average values, whereas these intervals are confidence intervals calculated at this level, means the average plus minus three sample standard deviations. And we use this data in such a way that we are refining against them independent atom model, this approaches utilizing pseudo-atom data banks, Hirschfeld atom refinement at two different levels of theory. And what we see that this bond is dependent on resolution, but above certain resolution, which is 36 degree diffraction angle, it's very much like results are very much like we are obtaining using other aspherical approaches. But the point is that IUCR recommendation for MOLE radiation is this one. So it should be changed. And we also have reference values from neutron diffraction, because we also got 14 neutron measurements on SXD at ISIS in Chilton, UK. And this rouge line, it comes from optimization of geometry in crystal. And when we take a look at the valence angles, the dependencies are more or less the same. If IUCR would recommend higher resolution, which these days the data collection is that fast that it doesn't matter. I mean, it's only a small increase of data collection time. And we can see that Hirschfeld atom refinement, these are the green results, is really very stable over the whole resolution range, even for small resolution data. It is giving results very close to neutron diffraction. In the case of bonds to hydrogen atoms, we see clear differences. I was mentioning the standardization normalization procedure. In this procedure, people were extending bonds to hydrogen atom from those obtained using independent atom model to the neutron ones, to these ones. Whereas when we are applying using Hirschfeld atom refinement, we already are getting neutron type bond lengths to hydrogen atoms. And when we think about hydrogen bonding, of course, these errors associated with position of hydrogen atom using independent atom model, they, in consequence, are giving us wrong distances in hydrogen bonding. But Hirschfeld atom refinement is giving very proper values, very close to neutron values of hydrogen bonding. But when we take the atomic displacement parameters, we see that there are systematic differences between atomic displacement, isotropic atomic displacement parameters, and those from Hirschfeld atom refinement and neutron refinement. And in the case of the lowest resolution, we had to use constraints because we were unable to refine freely this isotropic ADP for this hydrogen atom. So Actually, not only it's of course it's the best to use Hirschfeld atom refinement, then the results will be correct anyway. But when somebody is sticking to independent atom model, one should also correct temperature factors. And this is dependence for errors, for sample standard deviation and estimated standard deviation. Estimated standard deviations we are getting from least square procedures, but they are showing us they are smaller over the whole range of resolution, but they are only showing us how errors of the input variables are transmitting into the errors of the final results. And as we can see here, the smallest estimated standard deviations are, of course, for Hirschfeld atom refinement, but also the smallest errors, sample standard deviations resulting from multiple refinement, from multiple data sets, from repetition of measurements many times, are also the smallest. And so when you are getting ESDs from your refinement methods, please remember the true errors are bigger, at least 2 times bigger than those you are obtaining from least square method. And does this matter? All those tiny changes in values of hydrogen atom positions. Here you see dependence of cohesive energy or crystal lattice energy on used model of atomic electron density and on resolution. If we use neutron results as a reference system, we are getting this kind of energy, slightly less than minus 240 kilojoules per mole. For Hirschfeld atom refinement, we are getting results which are more or less 12 kilojoules per mole worse. But for independent atom model, we are getting results we are 50 kilojoules per mole in error. So this means that when we are using independent atom model, we can forget about weak interaction, hydrogen bonding, say pi-pi interaction, etc. However, when we standardize the data, we are getting these black points, which are in error slightly more, around 20 kilojoules per mole. And data banks are giving intermediary results between independent atom model and HAR. Hydrogen atoms in hydrides. We have studied several hydrides. You can see results in those papers. But I just want to show a few examples. Here we have 2 hydrogens attached directly to iron atom, to ruthenium atom here, and to rhodium atom. And so we have in total, like, I don't know, maybe 500 electrons, and those 2 electrons associated with those 2 hydrogen atoms. But still, we can refine them. And these are the distances to hydrogen atom. I mean, distances between heavy atom and hydrogen atom. And we've got neutron data for these systems, and so neutron results are these green ones, and Hirschfeld atom results are those red ones, and independent atom model are these ones. So even in such complex hydrides, even when we are refining against low resolution X-ray diffraction data, we are getting the values which are very much like neutron ones. And this is important. I mean, like 2-3 years ago, Professor Roald Hoffman was having a seminar within this series of lectures, and he was saying that there is no any experimental X-ray data for, say, very heavy atom hydrides which are superconducting. And in my opinion, with quantum crystallography, it should be possible to get experimental structures for such hydrides. And here is a distribution of CH bond lengths in transition metal derivatives. We've got from hard, this is this green distribution, from neutrons, this violet one, and the blue one from independent atom model. So clearly, quantum crystallography is giving proper distributions. In fact, because we can calculate this wave function at different levels of theory, at certain moment we have decided to verify whether we can attack really cool problems such as relativistic effects, and that was a part of a PhD thesis of Dr. Sylwia Pawlędzio, who is now at Oak Ridge National Laboratory. So she was studying this kind of system with which is a gold derivative, and we're struggling to get good quality data. And finally, we got them from Spring 8. And with this data, and we've got 0.45 angstrom resolution, and we performed HAR using lots of different refinements at different levels of theory, using restricted Kohn-Sham approach, using restricted Hartree-Fock approach, using relativistic basis sets and non-relativistic ones, applying anharmonic correction motion of accounting for anharmonic motion of the gold atom, and treating gold atom in harmonic approximation. So by taking differences in electron densities obtained at these different approaches, we can get information about consequences in electron density of anharmonicity, of electron correlation, and relativistic effects. And never mind numerical values, we can quantify them. We can get information how big are those effects. But the most interesting are distribution of changes in distribution of electrons. So these are differences in two electron density distributions showing relativistic effects. This means that relativistic effects at the gold atom are associated with shift of electron density to outer regions, and we have increase of electron density in the valence part of electron density distribution. In the case of electron correlation, we have electron density transfer to the neighboring atoms, and also localization of electron density close to the core electrons. And even more pronounced differences we can observe in Laplacian distributions. I do not want to go into details because we can see exactly up to what are the radial dependencies, how those two effects change. But if you are interested in details, you can go to those papers I mentioned at the beginning. And now, Hirschfeld refinement of ICE6 structure. ICE is my hobby. It's an incredible topic. You can see here that there are on water almost 10 million papers on water. On ICE6, on ICE in general, close to 5.5 million papers. On ICE6, more than 3.5 million. We really need a good artificial intelligence programs which would make a kind of summary out of those papers. No one can read even small fraction of them, which would give us something useful out of this all this literature. And of course, this immense amount of publications started from Kepler, Johannes Kepler, who wrote in 1611 a small booklet entitled The Six-Cornered Snowflake, which was originally published in Latin as New Year's Gift or On the Six-Cornered Snowflake. And he introduced there, using this cannonballs metaphor, closest packing, and these are the original drawings. And he was trying to explain the shape of snowflakes just by different arrangements of this cannonball-like water molecules. And isn't this amazing that in the 21st century, we still these are still cornerstones of say inorganic crystallography and mineralogy. I mean, in fact, all structures of ices are beautiful. There are more than 21 structures, the phases known, and in my opinion, at least equally many yet unknown. Here you see some examples of structures. Just take a look at this column. This is the space group symmetry of particular ice forms. It's really what a variety. It's P bar 1, it's triclinic, monoclinic, orthorhombic, tetragonal, cubic, rhombohedral. It's really incredible that ice is forming so different forms. Actually, in ice, each water molecule has 4 hydrogen bonded neighbors, and it forms 2 hydrogen bonds and is participating as an acceptor in other 2. And this is so-called ice rule, also called Bernal-Fowler rule. And at Caltech, there's Professor Ken Liebrecht, who is having a big collection of movies showing crystallization of ices. And those 2 movies are borrowed from this collection. And these are beautiful crystallization. One can spend days and nights watching how ice is crystallizing. And we also crystallize ice in diamond anvil cell. This is crystallization of mixed H2O D2O ice 6. And below is crystallization of D2O ice 6 in diamond anvil cell, different stages of this crystallization. And then we collected X-ray data at APS, and I can see Dongzhu among the participants of this this webinar. And once again, thank you very much for excellent help and work with this data collection. And in I6, which is crystallizing in P42/N MC space group, we have water molecules connected by hydrogen bonds, which form 2 separate interpenetrating but not interconnecting frameworks. And you can see them in 2 different colors. In this crystals, we have 2 independent water molecules. One is occupying a special position at the bar 4 axis with 1 independent hydrogen atom, and the other one is staying at symmetry plane, so thus it has 3 independent hydrogen atoms. So when you collect data, neutron data, and you refine them, you will see this kind of average structure. But what we did in our Hirschfeld atom refinement was with the convoluted, this average crystal structure, this average cluster of molecules into 259 different configurations. And you have illustration of 3 of them at this figure. And for each of them, we have calculated wave function, separate wave function, and we have averaged out wave functions and then got average electron density and applied Fourier transformation of this average electron density and got average spherical atomic scattering, Hirschfeld scattering factors, and use them in the refinement. And that is helping a lot, because even for laboratory source data, for D2O-I6, and also for synchrotron data from JESSICARS, we are getting results were very close, very much like those from neutron diffraction. And so the difference is only that small as 19 or 16,000 of angstrom. And in the case of H2O ice, we also are getting pretty good data. And not only this, we are getting anisotropic temperature factors, which are in errors when compared to neutron anisotropic temperature factors, only around 1.5%, 0.6%, 2.6%, and here 1.5%. So here they are. These are the neutron ADP values for hydrogen atoms. And these are our from different refinements. And in blue, you see the difference expressed in percent. And of course, for mixed ice, we have far big difference because we have 2 different sources of errors. As we have only 50% of one moiety and 50% of the other, and they have different thermal motions. So we are having those errors at this level. When we compare at the level of close to 9%, when we compare them with atomic displacement parameter of obtained for pure ice, D2O ice or H2O ice. We performed also similar studies for ice 7, and from the state of the art, these are the neutron refinements. In neutron refinement, people were getting this either single site model, and that's the outcome, or multiple site model with oxygen atom positions of the symmetry element, disordered ones, but purely using X-ray data and Hirschfeld atom refinement, and the same approach I described for I6, we got not worse results. We've got comparable results both for single site model and for for multiple oxygen position site model. Additionally, we were able to refine both disordered positions, I mean, isotropically disordered positions of hydrogen atoms and also disordered positions of oxygen atoms. And so we even went with this farther than those who were doing neutron diffraction studies. We also performed hexagonal ice studies using micro electron diffraction data. Here's a description of technical details. We've done also dynamical refinement of this. We used, I mean, fortunately, there is a simple relation between X-ray scattering factors and electron atomic form factors. And it's given by this relation, mod beta relation. So we use this, and that the quality of X-ray of electron diffraction data we obtained with our Glacios diffractometer. We perform refinement using firstly kinematic refinement and then Hirschfeld atom refinement using kinematic outcome as a starting point. And we've got pretty good data results. However, what really matters is performing dynamical refinement of the data, because the dynamical refinement gave us the values which are almost exactly the same as those from neutron refinement. So in conclusion, quantum crystallography is, in my opinion, is a game changer in structural research, including also high pressure investigations. Experimental electron densities allow for tracing tiny relocations of electron density. Hirschfeld atom refinement seems to be ideally suited for such subtle studies as structural investigations of different forms of ice, even in the case of laboratory X-ray diffraction data. So it brings ice research back to X-ray labs from large-scale facilities. There are proper relation between results obtained for pure ices and deuterated ices and structural and thermal parameters of mixed ices. I did not talk about, I forgot to remove this final conclusion because I did not talk about per distribution functions. But I want to say that by switching over to aspherical approaches, we can improve not only single crystal X-ray studies, we can improve powder diffraction refinements. We can improve per distribution function. We can improve macromolecular refinements. We can improve also XANES and EXAFS outcome. We can improve cryo-electron microscopy results. We can improve electron diffraction results. So actually, we can improve the quality of structural and data in general. And additionally, we can get electron density data, which are not accessible by when using independent atom model. And let me show people who were contributing to this research. And most of them, they come from my laboratory, but I also would like to thank those who work at APS, and especially Vitali and Dongzu Zhang. And also I want to acknowledge nice collaboration with Simon Grabowski and Florian Klemis. And also we are starting new collaboration regarding per distribution function studies of ices. And this is our group, what we call supergroup in Warsaw, and money comes from our national sources, grants. And let me finish by presenting this little story. Imagine that we are human electrons who live in the valence sphere of one big atom, the Earth. So when independent atom model is applied, that's really boring. There is nothing there, no information. But when quantum crystallographic approaches are used, we can see concentration of human electron density in big cities, depletion of human electron density in the mountains or in the deserts. And when we even increase resolution, we can see singular interactions between human electrons, love, friendship, curiosity, rage. So this is what quantum crystallography is about. It's about electron density, interactions, and with this, I would like to thank you for your attention and do apologize for extending this lecture for such a long time. Thank you very much.
Thank you very much, Christoph. That was a real tour de force. So there are a few people left. If you have questions, comments, please go ahead. Use the chat, unmute yourself, raise your hand.
I have one observation, Russ. Can I go ahead?
Yes, go ahead, please, Urshan.
Well, I want to congratulate, first of all, it was really, as you mentioned, is a tour de force. I was wondering, are you able to see that crystallography is slowly approaching to spectroscopy?
Well, I would say spectroscopy will always give us a kind of a complementary view, but there is a branch of quantum crystallography which is also utilizing some spectroscopic approaches. It's called dynamic quantum crystallography, and it's we should use as many approaches as possible, because each approach will give us like slightly different view at a given problem. So I'm fully for, and I was not showing spectroscopic results, but we also use them in our research.
Yeah, thank you.
Thank you. So Scott has a question. Should I read it? Can you comment on the minimum data quality needed for HAR to be useful or informative, particularly for limited opening angle DACs?
Well, this is a big advantage of Hirschfeld atom refinement, that you can really use low resolution data and still be getting reasonable results. As I was showing in the studies of this accuracy and precision, I mean, over the whole range of resolution, even for low resolution data, we can refine very good structures with HAR. And in the paper on Lang-Beinit, we discussed we're on purpose cutting out resolution, and we went up to say 50% completeness and very low resolution, and still were able to refine reasonable outcome. So this is the method. This is the method for studies of superconducting systems, for studies of say hydrogen storage materials, for studies of biochemical systems where hydrogen bonding is playing the role.
Yeah, that point struck me as well, that you don't need very high resolution methods to get that accuracy when you refine that way. I kept wondering at the very beginning when you would start introducing the problem of separating thermal effects from charge density effects, and you introduced that at the end, but it seems like that's relevant to some of the earlier analyses you discussed, for example, in hydrogen bond symmetrization, where there could be, thermal effects or dynamical disorder or static disorder that may be convoluted into the electron density that you map out.
Yeah, that's very very good question, because I mean this description of thermal motion, even in its analytical form, is very much like description of electron density. So actually, one should have like separate measurements in order to somehow deconvolute them in a proper way. And definitely to have studies as a function of temperature, just to see what is static, what is dynamic. And I mean, I'm looking forward to high pressure combined with temperature studies, because many DACs, it's so easy to use resistive heating or other types of heating and get good quality data up to very high temperatures. So this is opening new possibilities, and I'm really looking forward to more experiments, and looking forward to APS after refurbishment. I do hope that Jessicas will be supplying extremely good quality data, better even than this ID27, which is very good one.
That's right. Well, it's on track, and there are other facilities there at APS that are also doing those kinds of experiments. So thanks very much for a wonderful talk.
Thank you.
Congratulations on all this work, and thank you all for joining us.
Thank you.